Hello everyone, my name is Abdel-Rahman. Today I would like to run the example of a photon beam linear accelerator that comes with the EGSnrc. I'm hoping to demonstrate to you how to run such simulations using parallel processing to take full advantage of cores available on your machine. At the end, I would also would like to show you how you could analyze phasespace files that are generated from such simulations. So with EGSnrc, there is an example of a photon as well as for an electron mode linear accelerators. I'm going to do this with for the photon beam accelerator, and probably in the next session I will do the same for an electron for the electron linear accelerator. So the first thing we need to do is we need to copy the spec modules of the beam into a specific folder in our home area. That is going to be under EGSnrc. There's a subdirectory named BEAMVP, and then another subdirectory from that called Spec Modules. So if you go there and you list what's the contents there, what's over there, you will find already that these are example modules are available with the installation of EGSnrc. And I'm going to show you this spec modules. This actually is a linear accelerator for a photon beam. So the first thing you will need to do is to build and compile the spec modules. We can do it either using the graphical user interface, or we can do it from the terminal. So if we open the graphical user interface, it's you'll need to open BEAMNRC, and then you will select File, and you will select Load the previous accelerator. Notice that it will automatically open the directory under your home area that has the spec modules of beam. We're going to select the EX16MVp module, and I'm going to open it, and then it will prompt me to select a PEGS file. This is not necessarily now, so I'm going to hit cancel, and that is fine. Yes. Then we will go to execute and go to compile, and then we will hit build and compile, and I'm going to hit on compile. The first step is it has now created the directory, so it will create it again. So I'm listing it, it's here, and now it's it is in that directory. It's grabbing some macros, some stuff from the in-house directory, and making let's say the code, the beam code for this particular let's say accelerator. And the last step, it's going to compile that code and create an executable. So this will take some time, but we need to wait, and we should get a message shortly that compilation finished. Sometimes you will get a message that compilation failed. Just hit build and compile, and you'll get a message that nothing to update. You know, that's probably a bug on the graphical user interface. So now the message appeared, as I mentioned, compilation failed, but actually I think it was successful, because if you just hit on OK and hit build and compile again, you will get compilation completed successfully. Okay, we're going to close this, and let's go into that directory and see what do we have there. So the code actually, I think it's in this Mortran file, and this is basically it has the code for the linear accelerator, and that code needs an input file, and the input file for this demo accelerator or demo beam is available in the henhouse directory. So we need to copy a file, and that will be under henhouse, and then omega, and then you will find a beam NRC directory, and then it's going to be under the example beam examples, and there we should find listed the 4 examples that come with the EGS NRC package. And inside this folder, the EX16MV, there is an input file that we need to copy into our beam directory in our home area, and this file has the extension of EGS input. So we're going to copy that to this directory. I will list the command for you in the description for this video. So let's list again. This is now the input file. Now when I go and let's load the previous accelerator again, just to make sure, I'm going to select it, and I'm going to select it because to run AGS simulations you will need of course obviously the code, probably you will need an input file, and you will need a PEGS data file. The PEGS data file contains cross-section information for different materials that are going to be used in the simulation, as well as stopping power information required for transporting electrons and positrons. For this accelerator, we're going to use the PEGS data file in the henhouse, so browse henhouse, and we're going to select the 700 ICRU.PEGS for that. And the last thing is we need to load the previous input file, and that is going to be under the directory beam, and this is the EGS input file that we just copied into that folder. So after you have done this, you can actually see the preview the geometry of the accelerator. So this is the geometry of the accelerator. There is a target, primary collimator, flattening filter. This probably is a chamber. Actually, I'm reading them from here, from the spec module. So slabs, that's the target, primary collimator, flattening filter. This is the chamber. There is a mirror here, and we have the secondary jaws or movable collimator. So I think this is the X, and the other one is the Y, it's below it. And we have what else? We have an air, we have slabs here. This probably it's an exit PMMA, that's the exit window, and of course we have air all the way. Although I think this part, I think it should be a vacuum in within the primary collimator, and there should be an exit window somewhere here. Anyway, and they have air all the way to 100 centimeter from the target. One of the important outputs of a beam simulation is to collect particles that are going to reach this plane here, or any other plane. Actually, for this particular example, the plane defined to collect particles, that's what we call a phasespace file. It's defined below this component module on the slabs, and that's going at 100. To run the simulation, Just go to execute, hit run, and then we're going to hit execute. So the simulation is running now. I believe this is going to simulate 15,000 particles, 15 histories. That means electrons hitting the target of this linear accelerator. To change the number of histories that you're interested to simulate, before doing that, here is the summary of the simulation. The simulation took 14.2 seconds, and it's possible roughly to simulate about 3 million particles, between 3 and 4 million particles per hour. I mean, don't rely on this too much with such a small number of histories, but that just gives you an estimate of the time required to get, for example. So if I want to simulate 1 million, for example, and this tells me it's going to take 4 million probably per hour, then it's about 15 minutes to run 1 million histories. To change the number of histories that to run, we're going to close this window. We'll go to the edit domain, input parameters, and this is here the number of histories. So if I change this to 15, now 150,000, I'm going to expect it to take roughly 10 times more the time. So that's going to be about 140 seconds. So let's do that and save any changes that you do on the input parameters or in the input file. You need to save those. But now we're going to take advantage of parallel processing. In the previous simulation, the simulation was running on a single core. I have in this virtual machine 8 cores, so I want to actually split the simulation, do parallel processing. So the number of histories that are going to be simulated will be distributed among these 8 cores, and this means that we're going to, or the simulation is going to finish in a much shorter time. I'm going to actually launch it manually from the terminal. So to execute the simulation, just need to go to the terminal and type the following: EX, and then we'll type BEAM EX16MVp. That's the name of the code, and then the input file, which is EX16MVp. We don't need the extension, so we just leave it without an extension, because the extension, remember, for this input file is .EXSIMP, and we need to define the PEX data file, which is 700 ICRU. Now when I launch, this command will actually launch the simulation on a single core. So just to demonstrate this, there it is. So now it's just an interactive execution. We're seeing what's happening, but that's not what I want. So I'm going to kill that, and to launch it in the background with parallel processing, we need to, instead of EX, it's going to be EXB, and we need to tell we need to add the number of parallel jobs, and that will be, we'll add P equals to, and then we put P equals to 8, and we're going to hit enter. So you will find something like this: the jobs are submitted, and then if you hit top, you will see that now I have 8 running simulations for the code. So when we launched that command, the system duplicated the input file into 8 different input files, changing the seed in each of these files and executing the simulation. Now, to see the progress, there is a log file that is going to be generated. So more, and it will be called with the same name of the input file, and I think .log. So if you hit enter, it tells here is the information. These are the number of histories that have been simulated, and results are there, and these are the remaining. So we're almost there, almost finished. So more log. So now we're almost none, we don't have any remaining particles to be simulated. All the histories have been simulated and results were obtained. This log file will vanish. So if I'm expecting now, when I do more, this file, it's not there. So I'm going to do an ls minus la. See, I have 8 now. 8 this was my original input file, and it was duplicated with adding underscore w1 to the input file, and the results for that are in these 4 files, and then w2, w3, and so on. So depending on the split number that you decide to use, you will get those splitting will match that split number. The phase space file data is actually you will find them under a file with the same name, .EGSphsp1, and we have 8 of these. So these are 8 files that have particles resulting from the simulation. So the first thing, usually this is in particular for beam simulations, the first thing we want to do is to actually add or concatenate the particles that are particles in all of these 8 phase files. And to do that, I don't think there is a GUI for this. You will always need to come to the terminal. So it's going to be add phasespace, and we need to put the file name. We don't need the underscore w, just the initial file name. And what do we want that? So this is the input, and what's the output? I like to keep the output the same, and then I have to tell it how many phase space files we have. In my situation, I had 8, and then to start adding from which phase space file number. So I'm going to be 1, and then 1 is for because in a beam simulation you can actually have 3 different phase space files defined at 3 different levels. So in our case we had only 1, so that's why we have 1 here. So when I hit add phase space file, it will ask, should I override, because it seems from our previous simulation there was an original or initial phase space file for the first simulation that we ran. Obviously I want to override that, so I'm gonna type OW, and then now it has added all of these 8 phase files. To analyze the phase space file, there is another code, and I would recommend to use the graphical user interface. It's very nice. Is the BEAMVP. So BEAMNRC, that is to run simulations, to modify input files, to create beams, and BEAMVP is really to analyze phase space files. So we're gonna click on that, and the first thing I want to look at is, okay, let's list the parameters, okay, for some of these particles. So I'm going to start with 1. I'm going to leave the defaults, the particle type. Let's look at all, and then I'm going to select the phase space file. So we need it. It's in this one without the w underscore w1, and we're going to execute this. So in our file, we have about 40,000 particles. 26,000 of these are photons, the rest are electrons or positrons. It's the maximum number of particles, and this is the number of particles that were incident from the original source. We set up, I mean, in our simulation it was 15,000, 150,000, but I don't know why we have 400 are missing, but that's okay, still small fraction. And then this is now the list of data in the phasespace file. So in a phasespace file, we have every particle. We need a position to record the position. Of course, the plane is defined, or we know where the Z position, that's going to be at 100. But the X and Y position, that's the information recorded in the phasespace file. So the first thing is the energy, the charge of the particle. 0 is for photons, obviously, -1 is for electrons, and 1 is for positrons. This is the energy. Note that the energy is actually the total energy of the particle. So for photons, that's the photon energy, but for an electron particle, that is the total energy. So the kinetic energy is going to be the total energy minus the rest mass, which is 0.511 MeV. This is the X and Y position on at that plane. This is the direction of the particle, okay, or the cosines, I think, of the direction of the particle. Weight is this is the statistical weight of the particle, and there is some additional information which is called latch. It's like flags for the particle. Those can be triggered by either interactions and so on. It's a very useful tool to know, for example, did the particle hit the jaw? Did the particle interact in this location or not? I won't go through it now, but that's the information contained for each particle that is recorded in the phasespace file. And again, this is the list of, I think, the first 100 particles in the phasespace file. Another thing that is useful to look at is just okay, let's look at combine. Okay, where is it derive? Yes, so let's derive an X and Y scatter plot of particles from the phasespace file. So the particle type, let's look at photons, for example, and so I'm going to use, so within the phasespace file, remember the phasespace file is recorded at 100 centimeter. So I want to analyze particles, let's say from X from minus 30 up to 30, and Y minus 30 up to 30, and look at particles that have energy, minimum energy is 0 and maximum energy is going to be 16. I want all photons. And latch are those we can select. Do we want to look at particles that have this flag on or not? I'm going to select no for the time being. This is the phasespace file, and I'm going to just put XY output file name plot. Okay, and the maximum number of particles to plot. I want, let's say, all photons, so I'm going to put 30,000. If I remember, it was 26,000, so that's the total number of photons. So 30,000, that will include all photons, and we're going to hit execute. So it's running, and then of course if you're doing this in Linux, then it's going to automatically open to you this plot that shows the position of these photons at that plane. So we are at 100 from minus 30 to 30 in the X, and minus 30 to the Y. These are locations of all photons reaching that plane. One of the useful things one can obtain from phasespace file is to get the spectrum of the beam. So to do that, we'll go to the again here and select derive a spectral distribution from phasespace data. We want this for photons. We're gonna select the data, the files within that region, and this is the number of energy bins. I think maximum is 300. I like to go with 300, and from 0 up to 16. So this number is telling the system, look, equal bins between 0 MeV up to 16 MeV, and then go and analyze the energies of the particles in the phasespace file, and then count them and put them in those energy bins. And at the end, of course, you need to take into account their energy to derive the spectral beam spectrum. Latch, we're going to leave that as none. The phasespace file is fine, and I'm going to put here a spectrum, photon spectrum. Graph type, it can be either in a histogram or a point. I personally like point graphs, but many people prefer histogram plots, especially things that are related to Monte Carlo simulations. And the fluence type, I'm gonna select estimate real fluence, and let's execute the beam deal. The number of pins must be less than 200. Okay, so this needs to be 200. That's the maximum. I thought the maximum was 300. So execute this, and then we get, this is the beam spectrum. Okay, it's a bit noisy, and that's why we need to run more particles to reduce the noise in this graph. And that's the advantage. Again, this I like to emphasize this a lot, is running simulations in using parallel processing is really the way to go. If you don't have a dedicated Linux computer, I say, and your Windows or your Mac machine is powerful to accommodate having a virtual machine running on top of your Windows or Mac, then I think that is the way to go. You will get your results in lesser time. I hope this video demonstrated to all of you how to run or compile beam code. We have used the demo beam code for 16 MV photon beam that comes with EGS. We have demonstrated how to run a simulation with beam code, and taking advantage of parallel processing, although I believe that probably we need to do parallel processing from the terminal, not from the GUI. If you manage to do that from the graphical user interface, please leave some comment in the comment section. And then I've also shown you how to demonstrate how to analyze a phasespace file using the BEAMVP code. If you would like me to go over any particular part in more detail, please leave these in your comments. Next time I will run a simulation for the demo electron beam that is available with the EGSnrc. So please don't forget to subscribe and to like this video, share it with people who you feel are interested, and until next time, thank you very much.